Hello, everyone. My name is Sergei Sokolenko. I'm a product manager in the Google Cloud. And today with me, I have Thomas Weise from Lyft, from the streaming platform division. In today's session, we are going to take an overview of the components of a streaming solution, including Apache Beam, Dataflow, PubSub, Kafka, Spark. We're going to do a 30,000 feet overview. And then we're going to talk about improvements, what is new in these technologies, more specifically in Beam, Dataflow, and PubSub. Things like giving users more power, making streaming analytics easier to use, making streaming more portable. Then I'm going to invite Thomas to come in and share the story of Lyft using Apache Beam on Flink. And lastly, we have a couple of special announcements, so stick around. Hopefully, you'll find it useful. So let's get started. Let's look at the architecture of a stream analytics solution in GCP. And before I continue with the architecture, let me define what stream analytics means for me. There are two words here that are important: stream analytics. So it's a continuous ingestion and output of results. This is the streaming portion. Continuous is important. We don't micro-batch, we don't batch, we do continuous processing. And analytics refers to the fact that we don't just simply enrich a stream with some lookups and pass it through and store it. We do some analytical processing. Specifically, we group things by most often by time. And then we run statistical functions on it, sums, averages, more complex functions. So in GCP, you have multiple options for each of the steps of this streaming pipeline. Starting left to right, the things that generate events could include endpoint clients, mobile apps, websites, databases, IoT devices. You have to ingest this data, and you can use a couple of tools for it. You can use PubSub for streaming event ingestion. That's a managed Google service. And you can also use Apache Kafka, either self-managed or provided by the Confluent Cloud. All of these options are available in GCP. Now, once you ingested the data, you tend to start processing it. And if you prefer the Apache Beam framework that provides you with unified batch and streaming, that is portable, then you can run it on Cloud Dataflow. Cloud Dataflow uses Apache Beam as its SDK. If you're a fan of Flink or structured Spark streaming, you have options in Cloud Data Proc, which is another managed service provided by the Google Cloud. After ingesting and transformations of data or processing of data, you move into the storage and analysis phase. And here you have options for storing your data in a cloud data warehouse, such as BigQuery, or, for example, running predictions on the newly rebranded AI platform, aka CloudML engine. Or you can store your data in Bigtable, which is a great backend for dashboarding. Let me give you a couple of differentiation points between Apache Beam and Dataflow, kind of explain what the difference is. Apache Beam is the, actually I'll start with some historical overview. About several years ago, Google open sourced the Cloud Dataflow SDK. It became a top-level Apache project. Last year, in 2018, the Apache Software Foundation published some stats on all of their projects. There are about 200 of them. And it turns out that Beam is now the top, or was in 2018, the top Apache project by dev list activity. So lots of people are exchanging ideas, communicating. It was also the top 3 project by commits. Now, users like Beam because it provides unified streaming and batch APIs. You only need to learn one API and run your pipelines in batch and streaming mode. And the other big selling point of Beam is it's portable. And portability here refers to two things. Portability in execution environments. You can run the same pipeline, the same binary in Cloud Dataflow on the Google Cloud, or you can run it on, let's say, Flink on premises or in a different cloud. And there are other runners that are being created and developed. And the other aspect of portability is language portability. So it actually has two portions of it, or two aspects of it. First of all, we want to have the same API available across different languages, Java, Python, Scala, Go, and SQL. And the other aspect of language portability is being able to reuse and write your pipeline in different languages. So one team in your company could be working on I/O connectors and write them in Java, and the other portion of your development team could be writing things in Python, and you can combine them together in the same pipeline. So that's pretty powerful. We're going to have Thomas later on talking more about portability in his part of the talk. Now, Cloud Dataflow is the execution environment, one of the execution environments for Apache Beam. Dataflow uses Beam as its SDK. Dataflow is a fully managed serverless data processing service provided by Google. Together with Cloud PubSub, Dataflow takes care of exactly once or offers exactly once streaming semantics. What does it mean? It means that Dataflow takes care of processing your messages just once. It takes care of error handling and deduplication of data. The other benefit of Dataflow is it spends a lot of time on optimizing the processing time of your pipelines and resources used by your pipelines. It divides inputs, data inputs into small shards. It spans up resources, compute and storage resources. It then tracks how fast these resources are processing your small data shards, and it scales up and down depending on how fast the processing gets done and how parallelizable your inputs are. And lastly, the Dataflow team has invested quite a bit of time and energy in separating state storage from compute. And this allows us to scale the different components of the pipeline at different rates. This really improves our auto-scaling behavior. I'm going to talk more about this in a second. Let me also tell you a little bit more about Cloud PubSub. Cloud PubSub is Google's global messaging and ingestion event service. It allows customers not to worry about where their infrastructure is running. There's no provisioning needed. You create a topic, you create a subscription, and you can start globally, ingest data, and deliver data globally as well. Beyond streaming analytics, beyond data ingestion, you also can build a event-driven microservices architecture. You have access to push notifications. You can trigger things like Cloud Functions, App Engine, jobs, or Cloud Run applications. And lastly, because there's no provisioning involved or no scaling issues that you have to worry about, you are ready for production pretty much from day one. Now let's talk about what's new. And we bucketed the new things into three major investment areas or improvement areas. The first one is making our streaming technologies more powerful. And here we have improvements in auto-scaling, the separation of state storage from compute, providing a state service on the back end. This helps really, really well with auto-scaling. And then launching snapshots on the PubSub side, or in Cloud PubSub. On the ease of use front, we have improved our Create UI experience. I'm going to show you a quick demo. We have also launched the ability to use SQL to author and develop streaming pipelines. And not only can you have a stream and do some transformations on it, you can join static things like files and tables with a stream of events using SQL. And more than that, not just do we allow you this basic capability of joining, we actually embedded the user experience into the BigQuery UI. So if you are familiar with the BigQuery UI, you gain immediate access to Dataflow as the execution engine for your streaming pipelines, written in SQL. And lastly, we have also improved our monitoring and monitoring capabilities. So we inserted and created new user experiences in the job details page where you can track and monitor latency and data freshness and create alerts right from the job details page. And lastly, portability. So we're going to spend quite a bit of time today on portability. We're going to talk about how the Beam on Flink runner helps Lyft achieve their goals of being able to run Python jobs on Flink. Let's jump into the first area, more power, improvements in auto-scaling, state service, state storage. A few months, and actually before I do the the deep dive, let me talk briefly about the Dataflow architecture. In many cases, I introduce Dataflow to customers by telling them Dataflow is a black box. You really are exposed to it by connecting sources to sinks. You don't really have to worry about what's inside of this black box. But many folks do want to know what's inside the black box. And so let me just talk briefly about the innards of the service. Dataflow takes care of a lot of things like managing compute and storage resources, graph optimization, scheduling work, meaning dividing inputs into small pieces and assigning them to workers and scheduling this work. And we've done improvements in many, many places over the past 3 to 6 months. I'll just mention briefly compute and storage. We have launched the streaming engine in beta a few months ago. And this streaming engine feature is separating the storage of your pipeline state. It separates it from the worker nodes and moves it into a backend service. You'll see shortly how this helps with autoscaling. Then on the graph optimization side, we have launched yesterday the support for SQL as a means of expressing your streaming pipelines. We'll take a SQL statement and we transform it into a typical Beam graph that has inputs and outputs, joins and aggregations and windowing. And we will use exactly the right join conditions or join techniques to more efficiently process your data. Autoscaling was improved together with the streaming engine and the better handling of compute and storage and monitoring. I already mentioned the monitoring improvements. Now, the Dataflow streaming engine. I mentioned that a few months ago we launched the beta, so I'm actually very happy to announce today that we launched the streaming engine in GA. The streaming engine separates state storage from compute. What does it actually mean? It means that in the past we used to have GCE virtual machines where your user code was running, as well where all of our system tasks, or many of our system tasks were running. Things like storing the data elements associated with your streaming pipeline, with your time windows, storing the intermediate calculation results of groupings and joins. So in the past, all of this was stored in the same VM where your user code was running. And it worked in many cases, but what it didn't allow us to do well was scaling up or down smoothly. We did have support for autoscaling. Streaming autoscaling was available in beta, but this experience was a little bit choppy. With the streaming engine, though, with the movement of the state storage to the backend, we have a much better autoscaling experience out of the box. And these are the major benefits of the streaming engine: smoother autoscaling. What do I mean by smoother autoscaling? In the past, you might have seen our worker graph going from, let's say, 5 workers to 10 workers, and then maybe to 7 to 3. With the streaming engine, the shape of your adjustments of your resources is +1, +2, -1. So it's much smoother. You don't have these step graphs anymore. You have a much smoother graph of adjustment of your resources. We are using less worker resources, so your user code now has more access to more memory and CPU. And actually, our recommendation with the streaming engine, by the way, you don't have to change your code at all. You enable the streaming engine through a pipeline parameter. And once you do that, you can also downgrade your user workers from our standard recommended 4 core machines to 2 core machines, because we don't need as much CPU and memory anymore. We don't take it from a user code. I mentioned that we announced the general availability of streaming engine. We also announced the general availability of streaming autoscaling. The improvements in the streaming engine allowed us to also launch GA for streaming autoscaling. Streaming engine is available in 4 regions today. We are working on deploying it to every region, and pricing is based on the amount of data processed. So it's not the CPU and memory resources as in the past. It's actually how much data gets moved from user code to the streaming engine and back. Let's also talk about ease of use and improving the ease of our streaming technologies. Here we have the improvements in the Create Jobs UI. the monitoring graphs, developing SQL pipelines, and embedding SQL pipelines into BigQuery UI. Here's a screenshot of our jobs creation wizard. We offer more than 20 predefined templates today that connect sources such as BigQuery, Bigtable, Cloud Storage, PubSub, Data Store, and many, many more, JDBC, Cloud SQL, that connect these sources in simple single source, single sync ETL pipelines. You can also define some transformations in the middle. And so this is all available through a UI. You don't have to code anything. If you would like to start with these templates and extend them, we also offer you the source code for the templates. It's actually right in the wizard experience. There's a link to the source code on GitHub. So if you need to do more, you can always extend. Better insights, providing you better insights for monitoring and making it easier to get these insights. We now have graphs in the job details page which show you latency and data freshness, and you can create alerts based on both of these metrics. And let me actually give you a quick demo of how easy it is now to create alerts based on latency. Demo, please. So I have, before the demo, I've created a streaming pipeline. This pipeline reads from PubSub, and it windows data into 5-minute time windows, and it writes each time window into a file in GCS. As you see here, I have a graph of system latency and data freshness. There was a big spike in the beginning of the 8th hour, but since then, my latency pretty much stayed flat, which is great. So why don't I create an alert? I want to get notified if my latency really exceeds these maybe 10 seconds and jumps to values where I need to start paying attention. I can do it very easily now by clicking on Create Alerting, and I'll get rerouted to Stackdriver Monitoring, where most of the fields of my alert will be already pre-populated. I'm going to keep them pre-populated. Yes, I want my resource type to be a Dataflow job. The metric that I want to trigger on is system lag. I actually have a graph as well just to see what the latest values were, so that I'm more informed about the threshold that I'm picking. And I'm going to keep the job filter too. But the last thing that I wanted to change, or the only thing actually that I wanted to change, was the trigger condition. So I want whenever my system lag exceeds, let's say, 10 seconds, this is actually milliseconds, so I need to type in 10,000. So whenever my system lag exceeds 10 seconds of a period of 1 minute, I want to get notified. See how the graph moves here. And let me just click on Save. Yeah, that was all that I needed to do to create alerts. So now Stackdriver Monitoring will actually notify me whenever my latency exceeds 10 seconds. Back to slides, please. In addition to making it easier to monitor, we also improved the authoring experience for streaming pipelines. So for those of you who are familiar with Java or who are using the Java Beam SDK, in the past it was pretty involved to write a join statement. It took several lines of Java code. Here's a screenshot of a join using Java. I have 2 GCS files that I want to join and then output into another GCS file. Now, if you are familiar with Scala and are using the Shio package that was developed by one of our customers, Spotify, there's less code, it's less involved, it's cleaner, I like it. But if you think about it, SQL really solves this problem with 3 lines. Right? And so the idea was in the Beam community, why don't we bring the power of SQL to our users who need to do relatively common data transformations. And so the Beam SQL feature integrates with schema. It supports all kinds of joins. It supports both streaming and batch modes, can join streams and tables, and does lots of other good things. Yesterday, we announced the integration of SQL into the BigQuery UI. In addition to that, we also announced schema support for PubSub. So you can store a PubSub schema in a data catalog entity, and you can then, once you have the schema for a stream, you can do pretty much anything with it using SQL. So let me give you a demo. I'm just going to explain what's going on with the slide and then jump into a demo mode. In my demo, I'm going to take a stream of transactions. These are my typical sales transactions, the person who purchased the good, the sales amount, the product that was purchased, and let's say the city and the state where the sale occurred. So I'm going to take this stream of transactions. I'm going to attach a schema to it. And by attaching the schema, I'm now able to run SQL. Schema and SQL are mutually necessary. But the first step I'm going to do is I'm going to join and enrich my stream with an additional field. I want to enrich the stream with a sales region. And I'm going to use a mapping table in BigQuery to achieve this enrichment. Once I enriched my stream, I'm going to do windowing. I'm going to group data, and I'm going to create statistics every 5 seconds for sales regions. That's exactly what I'm going to show you in the demo. All right, I'm going to start in BigQuery. And for those of you who are familiar with BigQuery, you'll be happy to know that you now have access to running SQL statements against the Dataflow engine. I just need to select Dataflow engine in the query settings. And once I've done that, as you can see, there's a change in the UI. You now have a Create Dataflow Job button. I just need to type in a SQL statement. I'm cheating a little bit, and I have a SQL statement stored in Notepad just for the speed of the demo. So let me take it over, type it in here. This is the same statement I showed you on the slide. It takes a PubSub topic. This is not a table. This is a PubSub topic. It's a stream. And it joins actually with a table, with a BigQuery table. See how I did PubSub dot? It references a PubSub topic. And to reference a BigQuery table, I typed in BigQuery. Now let me also show you the schema support for PubSub. Once you selected the Dataflow engine as the execution backend, you get access to Dataflow sources. You can add more sources that you want to work with by going to Add Data. And we're going to find them. They're all stored in Data Catalog. I already done it before the demo, so I have a PubSub topic pinned in my project. And here's the schema of this PubSub topic. It has a timestamp. It has a couple of attributes, and it has a payload. And the payload is my sales transaction. It has things like the time of the transaction, the person who purchased the good, first name, last name, the city and the state of the sale, and the product and the amount. And in my SQL statement, I'm going to join it with my mapping table. And just to show you the schema of the mapping table, it's right here. It's very simple. It has state codes and sales regions. State code, sales region. And if you look into the preview, for example, the state of Missouri is mapped to my company's region 1, and the state of Delaware is region 2. So I have this mapping, and I reached my stream through a join. Now I want to start doing aggregations. And I want to do aggregations because I want to build a dashboard that shows me statistics for sales region every 5 seconds. And that's exactly what this grouping by operation does. It will group my data, and this is a streaming SQL extension. This is not available in standard SQL. It will create time windows of 5 seconds in duration and put all of the data elements in my stream into these windows, and then does whatever I need to do in my projections, which is summing up the amounts. So enough of me explaining. Let's actually run the job and see what happens. I'm going to choose the destination table. One of the things that Dataflow will ask me is, where do you want to store the results? and I'm going to store the results in a BigQuery table for right now. In the future, we're going to add more output types, but right now, everything goes to BigQuery. Actually, I used 25 previously, and I did a typo, made a typo. Yep. And within a couple of seconds, I get a job ID. It's a real Dataflow job. I can click on this job ID, and I will get rerouted to the Dataflow experience. It will take a minute or two to populate the middle screen, so I didn't want to wait for the demo. I actually launched the same query before the demo, and here's how it looks. If you open up the first box, you will see probably something that you would have expected. 2 inputs. One input will be from BigQuery. That's my mapping table. The other input is my stream, reading from PubSub. Then I have a join condition. And actually, the join will be chosen that is optimal for this particular type of a source sync combination. We're going to use a side input join. This is the quickest if I have a very small lookup. And then lastly, I have an aggregation that does the windowing piece. It will window data elements into 5-second windows. In the grouping portion, it will include the sales region. And at the end, everything will get written into my BigQuery table. Just to prove that there's data flowing, let's find out which table was used for my job. So I actually, in the previous job, I used the sales stats 22 table. I'm going to open up BigQuery again. I'm going to run a select star on this sales stats 22. Kind of pay attention to the timestamps. So right now it's 00 UTC, and let me rerun the query. And I'm going to get new statistics. So the SQL statement becomes not something static that in the past it's actually a living a breathing thing. It emits records every 5 seconds. It creates a streaming pipeline. Back to slides, please. So with this, I actually wanted to invite Thomas and talk more about portability and how Lyft is using this Beam capability in their own environment for, well, Thomas will share more for exactly what they're using.
Thank you. Thanks, Sergei. So at Lyft, we started to use Apache Beam and with Apache Flink. And we implemented a use case that I want to tell you about today. So Lyft is, probably many of you use ride sharing. I hope many of you like and use Lyft. Lyft is matching drivers and passengers for rides. And a lot of decisions need to be made fast and take into account traffic conditions and other factors to give a good experience to the riders and to the drivers as well. You see a few examples here, and I want to talk about the pricing part of it today. The use case that we implemented is dynamic pricing. And important to dynamic pricing is prime time. What is prime time? Prime time is basically a multiplier on the fare that you pay. It's not to actually make a lot of money, it's to balance supply and demand. Let's say in San Francisco, there's an event and a lot of people want to get a ride. How do we create the supply to match the demand, right? So you pay more, drivers can make more money, and drivers can, from further away, for example, can come to the place where there's more demand. The locations are identified by geohashes, and prime time is always applied to a location and a time. So this is really the use case, and how do we solve it? In the old system, we have architecture that consists of a series of cron jobs, essentially. They do computation in stages, and the results, the intermediate results of stages are stored in Redis to be handed between jobs. This is actually not an uncommon pattern of doing more complex computations in legacy architectures. The problem here is it's not a data graph or data flow. It's a stitched together, like in the old days of MapReduce, stitched together of multiple stages to arrive at the larger results. So data is taken from Kinesis, from PubSub, then aggregates are built, features, then models are executed on those results. And back and forth, we exchange the state through Redis. So what are the problems with that? First one, obviously, is latency. So let's say the stages are scheduled to be computed every minute, and we have 3 of them. So the minimum latency of this computation will be 3 minutes. That's pretty slow, depending on what the use case is. And in this case, it's critical to be faster. Then there is code complexity and operational complexity. You saw these the state-saving mechanism over Redis, and you saw then how these things need to be stitched together using cron jobs, and all of these things make a fairly brittle and complex infrastructure with a lot of boilerplate code, and it makes it hard to extend. We cannot easily change this structure. The final thing is it's not data-driven, really. It's time-driven. So at Lyft, we are using Flink for streaming. In the overall data architecture, we have many other tools, but for streaming, Flink is the engine of choice. And we use it to do declarative jobs, for example, for machine learning feature generation using SQL, Flink's SQL support. We also have jobs that are written with Flink's Java API. The question that the team that worked on the dynamic pricing asked is, how can we use this for our use case, because it's all written in Python. And Flink does not have a native Python API that allows you to run any workload that you would write with CPython. The solution for us was to use Beam, because Beam brings together multiple languages with different engines, and one of those engines is Flink. Flink has a runner in Beam. They transformed this cron job sequence to a pipeline, and this is just an outline. This is greatly simplified. We would have a data graph now with dependencies. For example, in the first stage, we read the events from Kinesis, then we do filtering, aggregation, and so on. And it's record by record. It's streaming, right? So now, as soon as we have an input, we can act on it, we can compute the output. No need to wait for a cron trigger that kicks off at some point. And no need for the intermediate results to be written to Redis as well. So there are gains. The latency obviously goes down. And the interesting thing about the latency is now that it is now dominated by the model executions, not by the infrastructure around it. And it can be reduced further by working really on the model executions. The model code was reused as is, so it was not changed at all. But the lines of code went down because we could remove all this boilerplate that was around it for scheduling, for the orchestration, and for the state saving. And this resulted also in a reduction of resources that are needed. So now I want to talk a little bit more about Beam and understand what is happening under the hood to enable such a use case. So as Sergei already explained, you have choices in Beam. It has 2 layers of choices or portability, the ability to move from one to the other. The engine portability, which was always there in Beam, that allows you to use different distributed processing frameworks, and also the language. So depending on the use case, you should be able to choose what the best language is, because they have different advantages and disadvantages depending on the context. So there are the users, there are the SDKs, and there are the runners in Beam. And what we are interested in here is particularly multi-language support. Beam started out when it became an Apache project with a Java SDK and Java runners. But in 2016, a very large effort started to make portability real in Beam, not just multiple engines, but also multiple languages, and that requires to cross the language boundary. It goes through all the layers, SDKs, framework, and runners. In 2017, the second language SDK appeared in Beam, and it was the Python SDK, and it worked on Dataflow only. In 2018, the first SDK that works portably was introduced, which is Go. And also last year, at the end of the year, the Flink runner, a new Flink runner that works with portability, reached the MVP stage. And what is currently being worked on is to also be able to combine elements from multiple SDKs in one pipeline. And of course, more runners to become portable, like the Spark runner. So here's an example of how you would write a Python pipeline with Beam. Simplified example, but it gives an overall impression how this would look like from a user's perspective, reading from a source, defining the windowing, defining when results are emitted, in this case with 3 different types of triggers. And then what the computation is, it's just a summation in this case, and then writing results out to a file. Sources and things are changeable. I mean, it can be streaming, it can be batch. So portability originally was Java to Java. Java pipelines written with the Java SDK, translated into Java object graphs that are understood by JVM-based runners. And with the exception of Python, which was understood by Dataflow only because there was a special translation for it. And SQL is actually a DSL that gets translated to Java. Now, Beam came much closer to what it aspires to be with multiple runners that support portability and therefore the ability to run other languages on it. And so on Flink, for example, we can run Python pipeline or Go pipeline. And we expect that more runners will support portability. Right now, there are still several that support the old translation path, which continues to exist. The key to being able to support other languages is to have a language-agnostic pipeline representation, which is done with protobuf. So now let's take a look at the Flink runner. As a Python user, you would write your pipeline similar to the example that I showed you, and then you would run your Python program like you would normally do. The interesting part here is a parameter that is a job endpoint, service endpoint, job endpoint that identifies the address to which to submit the pipeline. And that job service is hosted in a Flink runner. And the job of the Flink runner is to take the proto and translate it into a Flink job graph using the Flink API. Flink runner supports batch and streaming. And Flink has different API for batch and streaming currently, so there are different translations, but at the end, it's a Flink job graph that gets submitted to a Flink cluster. If you are familiar with Flink, then this will look pretty typical to you, except that on the Flink task managers, there are now Python processes, SDK workers, and they are necessary because we want to run Python code, and we cannot run the Python code in a JVM, at least not in a way that supports all the libraries that we want to use. So we have these extra worker processes, and they need to communicate with the Flink runner. And this is done through the FN services. FN services with different planes really orchestrate the executions. The endpoints are provided by the Flink runner, and the SDK worker uses the services to get its work done and receive the instructions. So as soon as we have extra processes and communication between those, the question arises how the performance will be, and this gets often asked. So this simple example pipeline is an overhead measurement. It's not, it doesn't contain any real workload. You can see that it has the empty lambda functions there. We want to know how costly this FN API is. You see at the bottom the Flink job graph that you would see in the UI, and it consists of 3 tasks. But the pipeline contains more transforms than that. So what Beam is already doing, it's collapsing transforms that are in a sequence together into so-called executable stages, fuse stages, and they are given then to the runner. The runner sees them as one operator. So you can see that there are 5 different transforms collapsed into one, which is only one interaction over the FN API instead of 5. So that's important, of course, for the performance. Then bundle size matters. If we talk about streaming, and every record is one thing that we can process separately. But going over the FN API, it's actually beneficial to provide a context for that processing that amortizes the per record cost over a larger number of records. And that's the bundle size. And in Flink, it's 1,000 records or 1 second, whichever occurs first. That's the default. Finally, we need to parallelize the SDK workers because Python can only run 1 thread at a time due to the global interpreter lock. So we need to run multiple of the workers to be able to match the parallelism that Flink provides. And then there are some optimizations that can be done on the Python side to further gain performance. Now, running this on machines with 16 cores and 16 workers, we can see that we get a good CPU utilization, what we were hoping to see. And with the default bundling, we get around 280K transforms per second per machine, which is per Python SDK worker process around 18,000. So to recap Beam portability, we can now write pipelines in non-JVM languages and still have them run on JVM runners like Flink. And Python on Flink is one example. The user code is fully isolated, so there is no restriction for the Python users, which libraries they can use. And the execution of those workers is also flexible. For example, the default is Docker. The default is Docker in Beam, and it's a very flexible way of deploying your dependencies. At Lyft, we are using a different way of running these processes because we already have the dependencies on all of the machines. We are using process-based direct process. And this is customizable, which is very helpful. The real final step in portability is to enable multiple languages in the same pipeline that lets us do interesting and necessary things. For example, we have a large collection of Java Beam I/O. Those are the connectors that connect to external systems, like reading from Kafka, writing to databases, and so on. And it's really hard to build these connectors in production quality. So we don't want to rewrite those. We would like to use the connectors that we already have with Python, and cross-language will provide that. There are other use cases, using TFX with Java, combining SQL with Python. Many more things become possible once that capability is in place. So with that, I will return.
Thanks, Thomas. All right, let's wrap up, and we have special announcements in just a second. Hopefully, I was able to show you the additional power, the ease of use, and portability. Thomas did a great talk on portability and Beam. A recap of announcements: streaming engine is now available in GA, latency monitoring and alerting is also available in GA. We have the Beam on Flink runner, and we have Dataflow SQL integrated into BigQuery UI. Not available just now, but it will be available in early May.